So welcome everyone to our 11th set of SRM talks. So first we'll have Dr. Claudia Wieners. So Claudia works in Earth system modeling and climate physics, and she has a sideline in economics and complexity, and her main research interest is to assess if and how solar geoengineering could help to mitigate climate change. So Claudia, if you want to go ahead.
Yeah, so I would like to talk about how not to do SAI, basically. So we'll look at scenarios where we burn fossil fuel like crazy, and then in 2080 we think, damn, it's too warm. So what could possibly go wrong with such a beautiful strategy? And yeah, I've done this work with a lot of people, including PhD students, Daniel and Jasper, who have helped run the simulations and analyze them. Brent is very much involved in the part on AMOC, which I will tell. And Fiona and Jessica and Cheryl have helped a lot with the ecology part, which will be at the end. Oops. Okay, so let's say we have done a really stupid thing. It is now 2080, and we have followed the RCP 8.5 scenario with strong greenhouse gas emissions and no SEI, obviously. And then suddenly in 2080, we think, shit, it's getting a bit warm. So we would like to cool down to 1.5 degrees, as Simone and others have told us could be possible with SEI in the Glenn scenario. Okay, so it's too hot. And now we just put as much SEI as to bring us down to that 1.5 degree scenario. So let's suppose we do that. Can we then get back our nice climate of SAI 2020? So could basically be the red line equal to the green line, not only for global mean surface temperature, but also for other variables we care about? Or have we messed up some things in an irreversible manner? So that's what I would like to discuss. And I will do that for two subsystems of the climate system. One is the AMOC, so Atlantic Meridional Overturning Circulation. And then we'll briefly discuss ecological systems too. Okay, so let's have a look at the delayed SEI and the AMOC. So for those of you who are not that familiar, let's briefly introduce AMOC. So basically AMOC is the distant heating for Europe. So there's in red warm surface currents that bring warm and salty water north in the Atlantic Ocean towards Europe. There the water loses heat, so it heats the surroundings, but it also becomes denser because the cooler seawater gets the colder, the denser it becomes. And eventually this water becomes so dense that it can sink down, which happens in the Nordic seas and around Greenland, including the Labrador Sea.
It hurts a little bit, but we're getting there.
Is there anything?
Okay.
Was there a question or something?
No, I'm just muting people, Claudia.
Okay.
Yeah. Sorry.
Okay. Fine. So warm water has arrived in the Nordic seas, and it sinks down, and then we get in blue here this deep recurrent current, which brings salty and now very cold water back to the south. It is debated whether AMOC may be a tipping element of the climate system. So it could be that making the water dense in the north may fail due to two processes. So one could be that the atmosphere warms, so there's less heat loss during winter, and that could make the surface water less dense and therefore less able to sink. Or alternatively, or additionally, the water may also become fresher, either because of changes in precipitation, so maybe under global warming there will be more precipitation in the Nordic regions, or also because of ice melt, either from Greenland that could start melting massively, or also a change in sea ice potentially. So here's a simulation from Van Westen et al., who also are at my institute. They have simulated AMOC collapse not under global warming, but by artificially dumping fresh water in the North Atlantic. And they found winter cooling in Northern Europe of way beyond 10 degrees. So yeah, 20 degrees cooling in February in Oslo. Well, as a caveat, it would maybe not be quite as bad under global warming, because the global warming could partially compensate the cooling by AMOC loss, but still this would be a very big change in climate if AMOC were to tip. However, models do generally not project AMOC to completely collapse. So most climate model project that AMOC will weaken substantially under global warming, but it is not clear whether it can indeed fully collapse or whether it would only weaken. So of course, if it's only weakening, this already could have significant impacts on the climate. Let's zoom in a bit on the processes in the North Atlantic, because as usual, things are a bit more complex than you first think. So in this plot, we have the current system. So the red arrows are surface currents, which are generally warm when they come in from the south and then lose heat while they whirl around the subpolar gyre. And then when you have sinking in the Nordic seas, but also around Greenland, then you develop deep currents, which bring this cold and salty water back to the south. And in purple, I've put the location where sinking happens. And sinking is here defined as a net downward movement of dense water. And importantly, sinking cannot happen in the ocean interior, so away from the coast. That's obvious if you look at the Sverdrup balance. So sinking in regions where geostrophic balance is present would require also very strong meridional velocities, and obviously we don't observe those. So this would be something like 150 Sverdrup worth of meridional velocity, so like 10 times as strong as AMOC. So we obviously don't have that. So the only explanation is that sinking happens in regions where geostrophic balance does not hold. So that's along the coast of Greenland and the Labrador Sea mainly. So you can have sinking when you have coastal currents that have the coast to their right and that densify along the way. So coastal currents that can get gradually cooler and denser. These coastal currents are strengthened by the North Atlantic subpolar gyre. So this is this counterclockwise circulation that we have here, let's say south of Greenland, and there's also a lesser branch which goes all the way around the Nordic seas and back along Greenland. So this is mostly a wind-driven circulation, but it is also strengthened by high density in the interior of the gyre. This has to do with thermal winds. So if the interior is dense, then the sea level in the middle will be lower, and this helps a cyclonic, so counterclockwise circulation. However, okay, if we need high density in the middle of the subpolar gyre, and if we also need to densify those coastal currents in order to allow sinking to keep AMOC going, how do we achieve exactly this high density? And here a second concept comes into play that also has to do with vertical motion, namely convection or vertical mixing. So the idea is that we have light water coming in from the south. So this water is pretty warm, even though it's salty. So it is light despite being salty because the temperature sort of dominates the vertical density difference. So warm and salty water over heavy, cold and relatively, but somewhat less salty water. Now suppose that this warm water cools by moving north and losing heat, especially during winter when the air is colder, then this water is still very salty, but it gradually cools down until the stratification, so the density difference in the vertical direction, gets lost. And what then happens is that pockets of very dense surface water sink down, but to compensate, then also pockets of slightly less dense deep water move up. So you have a strong mixing through the vertical column all the way to a certain depth called the mixed layer. So that's the depth at which the deep water again is so dense that the surface water cannot sink as deep. And this only happens, as I said, if we get enough densification, typically during winter, from the surface. This deep convection also helps to make the water column denser on the whole, because if you get these pockets of slightly less dense and yes, less dense deep water moving up, they can be exposed to extremely cold winter air and then sink down again. So you densify the whole water column by this process of convection. And note that this mixing that we're describing here is not the same as sinking that we've mentioned earlier. So during mixing, there is no net vertical movement. You just have pockets of cold, of surface water and deep water being vertically exchanged and exposed to cold air, where sinking really means a net downward movement, and the sinking is what happens at the coast. So let's map not just the sinking, that was these purple arrows, but let's also look at the deep convection. Deep convection happens in 3 areas: the interior of the Labrador Sea, the interior of the Irminger Sea, and then up in the Nordic Seas. But this does not happen directly at the coast where the sinking happens, but it happens somewhat more in the interior. So you could ask yourself then, how does this deep convection maybe help with the actual sinking that we need for AMOC? And well, there's 2 things. The first should become obvious from the previous slides. So we said that we need a great density in the interior of the subpolar gyre to get the subpolar gyre move and hence to have these coastal currents. And then in addition, the deep convection is also helpful in making the coastal currents themselves more dense. And it is believed that this is due to eddy exchange. So this water that has densified in the interior of the ocean moves into the coastal currents through eddy exchange and helps also to densify those. Now, I previously said that most climate models do not project AMOC collapse under global warming, but Scubin et al. And also follow-up studies found that there can be a separate tipping point that is not a full AMOC tipping, but this deep convection in the subpolar gyre can collapse separately from AMOC or ahead of AMOC. And the mechanism with which this happened is that if the subpolar gyre weakens for some reason, it will bring less salt from the subtropical oceans, which are very salty because of strong evaporation. But if you bring in less salt, then this will, if you bring in less salt near the surface, then this will lower the surface density. But a lower surface density makes it more difficult to have this winter convection. But again, we need the column of dense water in the middle of the subpolar gyre to keep the subpolar gyre going. So if you have less convection, we have less subpolar gyre. So there's a positive feedback process by which the subpolar gyre can be sort of gradually eroded. And this can happen in models without a full AMOC tipping, but it is still believed that a subpolar gyre collapse may weaken AMOC because AMOC and the subpolar gyre both conspire, so to say, to bring salty water in from the south. So with less subpolar gyre, we will have less salt import, and we will have less densification of that interior water that benefits the coastal current sinking.
Claudia, do you mean SPG, not SGP?
Yes. Subpolar gyre. Okay, so let's have a look how this plays out in simulations. So we have used the CSM model to model SAI, including very late SAI in the scenarios I've lined out in the beginning. Actually, we have not used what Simone did, namely the CSM vacuum model, but we have sort of emulated the aerosol fields into CSM CAM to save computation time. But anyway, so let's have a look at what happens to AMOC strengths. So I have here our 3 scenarios. Let's start with the RCP 8.5. That's the control scenario. That's the red line here. And if you look at a typical measure of AMOC strengths, namely the circulation strengths at 25 degrees north, we see that AMOC decreases by a factor of more than 2 from about 16 Sverdrup to roughly 7 Sverdrup or so. So you see that we extended our scenarios to 2130. So what we did was we followed the RCP 8.5 scenario until 2100 and then kept all the CO2 forcing constant. Now let's see what happens if we do early SAI. So like in the GLENS project, we use stratospheric aerosol injection to keep global mean surface temperature at 1.5 degree above pre-industrial. So we gradually increase the amount of SEI you use to keep temperature constant. And this also benefits AMOC. So that's the blue line here. You see that AMOC still weakens under SEI 2020, but the weakening is much less. So this is roughly in line what was also found by Tilmes et al. In the Glenn's follow-up project in CSM2. Interestingly, the SEI 2020 performs better for AMOC than SSP 1.26. So this red arrow is the spread of CSM simulations AMOC strengths taken from CMAP simulations that were done with the same model. And we see that the blue line has a much stronger AMOC than even the strong mitigation scenario. So
sorry, the colors are cut off. Could you tell us what the colors are again? Because I can't see them on the slide. They're just off the edge.
okay. So you can't see the legend then, or what's the issue? Sorry, what's
I
the
can see
I
the
can see
legend.
them.
I can see the legend, but I
Okay.
can't see the names of the colors on the legend.
Okay, maybe
I can.
I can see them.
Yeah, I can see
Yeah,
them
I can
fine.
see.
Well, with your screen.
So if
You
that's the
may
case,
have to
I
move
could
the
just
window.
make the PowerPoint a little bit smaller so that you can see the edges. Does it help? So can you now see everything? Can you now see everything or not?
I can see it just says SSP. Well, so if you just read it out verbally, so the blue line is which scenario?
The blue line is the SEI 2020, as you also see here on the left. The RCP is the red line, and then we have the late SEI, which comes now.
The late SR. Okay, that's fine. Thanks for clearing out.
Okay, right. So now here we have also the late SEI in green, SEI 2080, and you see that this does stop further AMOC weakening compared to the red line, but it also does not restore AMOC to the levels that would have been possible under SEI 20. So in other words, even if you restore global mean surface temperature, you do not restore AMOC strengths. So apparently there are some long-term AMOC change that are locked in by having waited sort of too long with the SEI. And obviously this also has impacts on the temperature distribution. So this is the temperature change in Kelvin with respect to present day, so to say. So you see that in SEI 2080, the North Atlantic is overcooled compared to what would have been achievable in SEI 2020. So even in SEI 2020, you see here a cold blob, so to say, due to AMOC reduction, but it's much more pronounced in SEI 2080. We did not investigate whether this AMOC weakening under late SEI is sort of truly irreversible or just a decade-long issue. So it could be that if you simulate another 100 years or so, that eventually the blue and the green line would converge. We have not tried that. But even if it's just for a few decades, this is still a societally very relevant timescale. So we have at least a prolonged and potentially really irreversible AMOC change that we incurred due to waiting with the SEI. Now we wanted to zoom in a bit more into the processes that may be relevant for AMOC, and so we zoomed in the steep convection issue. In this plot here, you see for present day, so let's say 2020 to 2040, the regions which have the steep convection. We measured this by the mixed layer depths, MLD, which goes up to something like 1 kilometer, so 1,000 meters. And so this is at the end of winter after convection has taken place. So this is mixed layer depths in April, which we use as an indicator. And we see that deep convection happens in 3 regions, namely the Labrador Sea, Erminger Sea and Iceland Basin, and the Nordic Seas. Now let's see how this changes under SEI. So first, if you look at the control, we see that deep convection ceases in all the deep convection regions, so there is no red spots left at all. If we apply SEI from 2020 onwards, we still lose the deep convection in the Labrador Sea, but we keep deep convection at least partially in the Erminger Sea, and we keep it or even slightly strengthen it in the Nordic seas. Now under SAI 2080, so the late SAI, we have not restored deep convection anywhere. So there's a tipping point, at least in the deep convection, even if maybe not fully in AMOC itself. You can also see this in time series. So here I have time series of deep convection in the Labrador Sea, the Irminger Sea, and the Nordic Sea. Again, red is control, blue is SAI 2020, and green is SAI 2080. So in the Labrador Sea, no matter what you do, deep convection is lost. So the only thing that SAI 2020 can do for you is to slightly delay this loss. And SAI 2080 will also not restore it. In the Irminger Sea, under control, you also lose deep convection somewhat later than in Labrador, and it's not restored by SAI 2080. But in SAI 2020, you keep deep convection, even though it becomes very, somewhat weaker and very variable. And in the Nordic seas, deep convection strengthens under SAI 2020, under control, so the RCP 8.5. It happens to just about collapse at the time that the SAI starts. And under SAI 2080, you see that there's a temporary revival, but eventually deep convection is lost as well. Now we thought about two possible mechanisms which could cause this. One of them is the basic salt advection feedback of AMOC reduction. So it could be that with AMOC gradually weakening and the subpolar gyre also weakening, that at some stage there simply is not enough salt anymore to have deep convection, and SAI doesn't help this sufficiently because we already passed a tipping point. And the second potential mechanism that we thought of is sea ice formation. So you see here that in SAI 2080, there's a lot of sea ice in the former convection regions, which, by the way, are not present under control because control is so much warmer. And sea ice can, of course, block the contact between the ocean water and the cold winter air. So the sea ice may additionally sort of seal off the ocean against winter cooling and thereby prevent convection from happening. So we were wondering, is SAI sort of self-defeating by promoting sea ice if convection is already weakened or lost? So let's have a look at the sea ice mechanism first. And we looked in particular in the Labrador Sea and the Nordic seas. So in the Labrador Sea and the SAI 2080, you see here that sea ice starts to come eventually, but it only comes in once the SAI starts, because the SAI brings additional cooling. And this is at the moment where the mixed layer depth has already for a long time been reduced. So sea ice only forms after convection has been sort of dead for 30 years. So you can definitely not blame the sea ice for killing the convection. But the sea ice mechanism may help to sort of prevent SAI from kickstarting deep convection again through surface cooling. Now we also had to look at the Nordic seas. So again, this is plots for the SAI 2080 scenario. So you see that there's here this temporary revival of deep convection after SAI starts, which we have not seen for the control. But if you now look at when sea ice starts, you see sea ice again starts when deep convection is really more or less dying. So this again suggests that sea ice is not the cause of the convection shutdown, but rather a consequence. The idea being that if the convection stops, then you can form a layer of very fresh surface water. So it's light because it's quite fresh, but it's also cool. So it allows the sea ice to come, whereas convection would allow somewhat warmer subsurface water to come up during winter and prevent the sea ice. However, you could still think that maybe sea ice again seals off the ocean against the cold winter air and thereby stabilizes the dead state. Then we also look at the alternative idea that it's just the salt advection feedback that prevents convection. So to do that, we had to look again in the SAI 2080 scenario on temperature and salinity in the Nordic Sea region. So this is the depth profile of temperature, and in the moment salinity comes as well. So here's the time where we have this temporary survival of convection under SAI. But once this convection reduces, there's a strong surface cooling, which is partially due to the direct effect of SEI and partially due to that feedback that once convection stops, you allow an isolated surface layer to be exposed to winter air. So you may think that surface cooling is in principle good to start convection. However, there's also the effect on salinity. So you see not only a surface cooling, but also a surface freshening, which may be partly due to lack from large-scale advection and partly also a feedback process from the reduction of convection. And of course, freshening is bad for reviving convection.
Claudia,
Yes.
2 more minutes, is that okay?
It's fine. I mean, we started also a bit later on.
Yeah, sure. Okay, cool, thanks.
Okay. So if you look here in this plot, you see that we are in a, so this is the colors are densities, how they depend on temperature and salinity. And we see that we are in a regime where the density is very much dominated by temperature, so that winter cooling doesn't really help to start convection. It's the salinity which matters. And if you look at large-scale salinity import into the North Atlantic, you see it goes down a lot, which is probably partly due to feedback coupling with overall AMOC weakening. So basically, the North Atlantic, including the Nordic seas, has already become too fresh to restart the convection. So we see that in our model, AMOC significantly weakens under RCP 8.5. As early SEI can prevent AMOC weakening, not perfectly, but quite a lot. Late SEI cannot. So it slightly helps, but it does not restore AMOC. And in particular, also, late SEI does not prevent that tipping of that convection in the subpolar gyre. And we think that salt advection feedback is the main process, but maybe SEI helps to stabilize the no convection state. As a caveat, this is somewhat model dependent, so not all models have this SPG collapse under RCP 8.5. And now I'll be very quick, but we also had a bit of a look at ecosystem reversible, sort of effect of SEI on ecosystems. So let's skip this part. But we had a look at how climate zones, so from Köppen climate zones, shift under early and late SEIs. So here these are different climate zones like tropical rainforest, tundra, and so forth. And we see that if we just have the RCP 8.5 scenario, then 34% of the land area changes their climate zone, which is probably bad for the ecosystems that live there. If you do SEI early from 2020 onwards, you can strongly reduce the amount of area that goes to new climate classification. And at first you may think that, well, SEI 2080 is doing a quite good job because now we only have 14% of land surface that changes climate zone. So late cooling restores your climate zone. And well, that's true. But the problem is if you're an ecosystem that there's an intermediate overshoot through which you go. So if you look at a more complex map, we see in green, these are areas that have changed their climate zone by 2080. So before you start the SEI, and then have changed back. So basically ecological systems, they experience a kind of roller coaster of warming and subsequent cooling. So we speculate that, again, delaying SEI may cause irreversible damage to ecological system, even though formally, so to say, the climate zone has been restored by the SEI. So to come to overall conclusions, tipping points and irreversible changes are believed to be among the most threatening aspects of climate change. However, there's been very little research done on what SEI or SRM more generally could do to climate tipping, so this may be slowly changing. In many cases, one can at least try to guess the effect of SEI on processes that drive tipping, for example, temperature. But there is very little known about whether SEI could change tipping that has sort of already started or even be completed. So for example, if you wait too long with doing the SEI. So our preliminary results suggest that for some subsystems, like for example AMOC, there's at least some amount of irreversibility involved. So this may seem to suggest from a pure climate physics perspective that if you need SAI, you should not wait, but start as quickly as you can to prevent tipping or irreversibility. But of course, that's a very isolated way of looking at it. And there are also political aspects of which I think Daniele may tell us more. Thank you very much.
Excellent. Thanks, Claudia. In the interest of time, I think we're just going to move straight to Dan's talk. And if there are any questions for Claudia's talk, we can take them after Dan's talk, because I think Dan has to leave on the hour sharp. So we'll just move on to Dan. Do you want to share your slides?
Mm-hmm.
And I'll just introduce you briefly. So Dan Visioni is a climate scientist and assistant professor at Cornell University in the Department of Earth and Atmospheric Science. And today he'll be talking about how to assess SRM in the international stage, what does it mean, and where are we, and it's a perspective between science and politics. So take it away.
Yeah, thank you. Thank you, Matthew and Simone, for the invite. So today I will probably be not as interesting as Claudia from any perspective. I'm not going to talk about science at all. I don't have results to show, but I felt like it was high time to sort of present some of these. I think there's a lot of things happening in this field, and not everybody is all the time aware of what is happening. So I just thought it was good to, first of all, give a brief perspective about the things that happened in the last 6, 9, 12 months and where things are headed, and then give a very personal, in this case, perspective about where I think we as a field should go towards to sort of catch up with all of this. So, well, lots of things happen. I feel like everything is happening all at once, as usual. So in a way, the last report, in this case, an expert review of SRM research and deployment, was this very brief report from UNEP, the United Nations Environment Program. It had a lot of experts reviewing this. It was quite brief. It was the first time that UNEP officially engaged with the topic. I mean, it's a great report, very balanced, and quite surprising that that UNEP came up with it. It also got quite a bit of pushback, as I'll try to talk later. But in a way, this is sort of the last thing that we saw. There was no new science at all. It was just a reassessment of sort of all the things that research had done. There was a good Q&A, so it's a good entry point, I think. But it is not an actual assessment. What happened after? Well, in the summer of last year, there was a meeting in Kigali by the WCRP, the World Climate Research Program. And all the people that were there, all the representatives and the parties wrote this declaration, this Kigali declaration that was signed in January, called Climate Science for a Sustainable Future for All. And the kind of great big thing that was there was that there was this part that explicitly says that there needs to be strategies for research to inform policy about risks and possible benefits of SRM. Already the fact that it says risks and possible benefits is actually quite huge compared to previous discussions. And it explicitly says that the world needs to build an effective transdisciplinary research program, and that WCRP must be active in this research domain, and it must position itself as the honest broker, as a respected community voice in assessing and synthesizing, so playing a major role in establishing an assessment process. This is why then the WCRP set up this LAEROS activity on climate intervention research. Again, the words are transdisciplinary research effort. And well, the reason why I mentioned this is also because I am the co-chair. I was elected by the Joint Scientific Steering Committee of the WCRP to co-chair this effort that includes both SRM and CDR. So in a way, it was considered like a very big move for the WCRP to explicitly say we do need more research in this area, that this research needs to be global, that this research needs to be transdisciplinary, and kind of needs to meet society's urgent need for robust and actionable climate information in this area. I put the website here, you can go take a look, but there's a lot of things. Well, there's a one-pager that sort of a high-level review of what the Lighthouse activity is going to do. You can see sustainably scaling up the potential of climate intervention, rigorous, transparent, and globally inclusive research is a big focus. And in a way, the WSRP wants to position itself as the basis for such an assessment, which doesn't mean, and that's kind of a big point going forward, it doesn't mean that the WCRP is claiming that the WCRP can produce such an assessment, but that such an assessment needs robust research bases that perhaps the collective expertise of the World Climate Research Program can provide. So this means evaluating literature, identifying scenarios, environmental consequences, uncertainties, knowledge gaps. We have a document on knowledge gaps coming later in the summer. And the most important thing is that it sort of positioning itself as the location where it will ensure that research will be conducted in a transparent way with open access to data results and the model used to assess interventions and their impacts. So kind of this big theme of transparency I'm going to pick up right after. Well, right after that, actually, a week after the WCRP Lighthouse activity was announced, there was this United Nations Environmental Agency Assembly meeting. This was the 6th meeting, and it was the 2nd meeting at which Switzerland proposed an actual assessment. They proposed an ad hoc group of experts to produce a detailed assessment report of SRM. They had already done it at UNEA 5. It got quickly shut down. It also included CDR. In this case, they were much more focused on SRM because that was sort of the message. And there was a lot of discussion that ensued after the Swiss proposal. There were a lot of differing opinions. There were many countries that actually mentioned moratoriums on deployment. They say, following the Convention on Biodiversity, that, however, explicitly says that there's a moratorium on geoengineering if it threatens biodiversity, and so it should not be. It was never meant to be also a ban or moratorium on experiment, or outdoor experiment, as some group keep repeating. There were also some countries that said UNEP is useless. UNEA only has control over UNEP. And some countries like the US said, well, the WCRP has had this new lighthouse activity. They should do it. There's no need for UNEP to duplicate the effort. There were, again, a lot of concerns about moral hazard, especially from African countries, but also there was a lot of people have interpreted all the discussion going on based on what high-level things came out of that as, there was a hostility and nobody wanted to talk about research. But actually, if you go look at what happened in the discussions, there were a lot of requests and from countries like in South America and in Africa saying, well, do our scientists have actual access to the research that is going on? Is this research being inclusive? Are our countries being considered? And especially Brazil, I think, had something very explicit about capacity building and the fact that there could not be such a report, especially if the group of experts ended up being quite exclusively focused on the global north. There was this idea floated towards the end when it was clear there was going to be no agreement whatsoever on the assessment, at least to have a research repository. This was an actual proposal that came from African countries, so it's pretty hard to say. It's pretty difficult to say that they were completely opposed to research because they had this idea of a research repository. Of course, then there was discussion about what constitutes research that goes into this repository, who holds it, what's the purpose of that. So nothing happened at the end, but the fact that it went up to this point, I find it incredibly positive because it means that countries are willing to discuss this issue, but especially that they have some actual real concerns that I think we should address going forward, especially as the next UNEA meeting is going to be at the end of 2025. So, back in March, I said it was a year and almost 2 years. Now there's a year and 5 months, but I think it's still a good time to start doing some of these things. Finally, the last thing, of course, this is not meant to be comprehensive, but finally, the last thing is that the IPCC had a call for nomination for experts to draft the outline of AR7, of the next assessment report that is going to happen around 2028, 2029. And in the cross-cutting areas, so this is not in working group 1, 2, or 3, but in all 3, there was the request for experts that are experts in carbon removal and SRM and associated impacts and feedbacks. So this means that there is the opportunity at the scoping meeting in Kuala Lumpur in December of this year to perhaps, if there is agreement, to have a cross-cutting chapter on SRM. This coupled with the fact that on the modeling side, there are the new experiments that are coming out for AR7, and there's tons of MIPS, of model intercomparison projects, tons of experiments proposed. So up to the point where CMIP had to sort of have a fast track, the climate model intercomparison project had to have a fast track of experiments that they think modeling centers should prioritize in order for some of these results to end up in the working group 1. And GeoMIP was approved to have one of these fast track experiments. The name is not settled, but these all happen very fast. So, but the main point is now modeling centers know that this is an experiment with sort of priority in a way, not because it's more important, but because it's considered policy relevant and something that must be included, especially in working group 1, that is the one that comes first. So I think this is all encouraging from the IPCC side. So what's next? Well, again, it looks like there's a lot of things going on, but there's also a lot of discussions, right? One of them, again, being what kind of research goes into an assessment. This was a big point at UNEA, and the IPCC clearly made the point that this is not just a physical science problem, so it's not going to be just a working group 1 issue, but the research that goes into an assessment should also look at governance, ethics, environmental impacts, societal impacts, and so on. There's a lot of discussion over should an assessment precede governance efforts, go together with it, or come before it. I'll say maybe where I stand on this, but this is another thing that people discuss a lot. Should we have strong regulations in place because before we move on with the research? This is clearly the research is already happening. So who does the assessment is also another thing that's going to be important. UNEP has representatives and experts that are decided by the countries. The IPCC is a bit more a bottom-up effort from scientists, even though they are nominated by the countries. So there's a lot of ground there as well. And then the big question is sort of, well, what's the assessment for, and what happens after the assessment? Is the assessment a way to, quote unquote, kill SRM, or is the assessment something it's something that continues? And there's one, just like the assessment reports, there's one, but eventually it does move us closer or further from a potential future deployment. So, and this is sort of the excuse for this talk. When Matthew invited me, it was recently we published this commentary with my postdoc Hilaria and Isabel from Utrecht, from Delft, where we commented on this paper on GRL by Sandro Vattioni et al., where they looked at different injection material for SAI. And we kind of used this opportunity to discuss some of the issues with all of these, right? And in a way saying, well, if we're talking about different materials and people sort of, it's not a choice, it's not a race at who has the best material, but it is a discussion over, eventually one would have to say, what has more risks, what has less impacts. And so we kind of used this commentary to discuss some of the things that I'm going to talk about here and just expand on them. And again, I think, so I'm kind of dividing this in sort of 3 areas. There are 3 things that I think we should really prioritize without thinking about what actual sensors are going to do, right? And one of them is accessibility. This was a clear, strong message from UNEA, from UNEA, and so we should really be more careful about this. What do I mean by accessibility? Well, for now, there are essentially 2 ways to access results about SRM modeling. One of them is the Earth System Grid Federation nodes. So this is where all the CMIP6 output is. it is really not that easy to navigate, and calling this a repository, like, if you have to download the data, it's not very easy to use. So it's very hard to claim that this is a way to have accessibility, especially in places with slow internet connection. The other one is, this is an example from the simulations that we ran with Yaga 2 years ago. They are available online, not all of them. And again, when people want to look at things like downscale data or sub-daily output, it's very hard to give them access. So this is sort of the question of, well, does everybody have the tool? Do people actually have the tools to conduct the research they would like to conduct? And if they don't, what do we do? And this is also sort of where I hope the WCRP can act as an accelerator for this kind of discussion. So how do we deal with this large amount of produced data? And there's going to be more. And how we distribute the data, but also validate it, right? If you're doing sub-daily, if you're doing downscale data, there's a lot of questions that we still need to solve, I think, if we're trying to understand more regional downscaled impact, to understand whether our models are telling us meaningful things about it. So I think that there's some very preliminary efforts, but this is a big area where I think we should do more. An example, for instance, NASA did provide some downscale climate projection for CMIP6, not for GeoMIP, just for future climate projections. And I found it interesting that they had some really big caveats, right? They said this is only to be used for scientific research, no commercial application, no engineering or design studies. Community feedback is required to improve and validate the data sets. And so I imagine something like this could happen. And this is clearly an area where I really think we should focus a lot more. There's definitely a lot of merit also in allowing people to think through scenarios better and without having just a bunch of modelers decide that. I think that in GeoMIP, we're trying to make a real big effort to have more people involved in the process of scenario generation. But having something like emulators, climate change as En-ROADS, for instance, or something like that, they are not going to replace climate models, but they're a useful tool for people to understand by themselves without being told by others about the impacts. The second thing is transparency. I think that transparency is, that's what people and countries are demanding more and more of. Transparency does include a repository of research, not only of research that has been done, but also perhaps of research that people are doing or that people want to do. Sort of something that allows people to have a clear idea about where this field is headed. Again, and for this, when we were writing the commentary, one of the reviewers really pointed out, and I think it was fair, how hard and time-consuming this is. I agree 100%, but I think it's also necessary. And so this is clearly something that funders should be made aware of, whether they're private or public, about the fact that doing this act of transparency, I think it's positive, but also it's going to take a lot of work and needs to be supported. To me, transparency also means reasons behind research choices. As an example, we're trying with GeoMIP. I think we're trying very hard for this paper that we had to describe the experiment that is going to be in the fast track. We spent a lot of time discussing all the decisions that need to be made in a scenario, why we made decisions that we decided to make, opened it up for discussion. None means that we're going to be perfect, but I think it's a good step forward. And I really hope that it's something that people follow more, perhaps by pre-registering modeling experiments and what they expect modeling experiments to do. I'm going to go back to that later. So for instance, why are we simulating the scenarios we use? Why are we supporting the experiments we propose? And why are we researching these instead of something else? I feel like there's a lot of, I think this is also important for transparency, and saying, well, we're not doing this research just because we're curious about it. Maybe some are, but we're doing this research because we think it might be urgent to give this kind of information. And so being more outspoken about this, I think is going to help overall. Finally, I also think that transparency means having a repository of funding sources and of intents behind those funding sources. This is clearly contentious, but I also think that it's unavoidable. There's a lot of good reasons why I think that, but I think that, a repository is not just a repository like, look, here's the model data, but a lot more than that. and countries are really demanding this. And so if we do it as a community before we're demanded to, I think it's going to be a great move. And finally, transparency in results communication, efforts to actually explain the research to the audience. I mean, something like these open to all seminars are clearly a good example, but there's a lot more that I think could be done there to make sure that people are actually informed. I was doing an interview at the radio a month ago, and the host will kind of ask me, why aren't we talking more about this? We should be informed. We should be informed to make the decision. And I perfectly agree, but a lot of people maybe don't. But this is clearly something that we should be talking more of. As an example, today, this article by James Semple in MIT Tech Review came out where he kind of talked about nonprofit that are funding geoengineering research. I think it was an excellent article. He talks about a lot of these funders. I think this is great, but what was the quote about all of these? There was a quote saying, well, scientists are not going to be keen on producing something that seems contrary to what you thought the grant maker was looking for. I think if somebody said this about climate change research, it would consider it incredibly offensive. But when it comes to SRM, everything's game to insult researchers and assume that they're too weak-willed to actually publish what they want. I think that's very dumb. But also, I think that clearly having clear communications by the funders and by those that have been funded about what the goal of the research is could at least prevent that. There's always going to be criticism, but some criticism I think could be really averted by us being more transparent. Finally, science, of course. The center of an assessment and the center of our research is science, and we do need more robust science for fundamentally reason. Meaningful decision, and these are all things that we should be pretty also stronger in communicating. Meaningful decisions can only come from having robust information. People are going to make decisions about this field anyway. What we can provide as a field is robust information and trusted science that can make those decisions informed. The alternative here is not between making decisions or not making decisions about SRM, but it's about making decisions about making informed decisions versus making uninformed decisions. However, it's true that trustworthy science takes more than just good physics. There's not going to be a way to demonstrate mathematically that our models are good or that our experiments are good and they're trustworthy. It also requires trust. And so this is something that we should keep in mind, even if we're doing what we consider to be basic research. But also, and I think this is getting more and more important, I do believe that good science comes from free scientists. And so I think, and I'm trying to do that a lot more, that we should more radically defend scientific freedom against attacks and assuming that somebody can govern from the outside and tell us what to research explicitly. This doesn't mean that research in itself is neutral. We need to acknowledge that doing research is a moral choice, but also we should be more forceful. And I'm trying to convince as many people as possible of this also at the AGU ethical principle process that really we should defend free science a lot more. And the alternative is pretty clear. We always assume that governance efforts are going to come from people from our side and they're going to have good intent. But there's plenty of examples. Florida saying we cannot say climate change anymore. Florida saying the lab-grown meat should be banned. Those are also things that are defended as being ethical or coming from the spirituality of the people that are in this case Florida, but not speaking on Florida, Italy, same issues. And so if we forget to defend scientific research for the things that matter, we're just opening the side to more and more attacks to all of science. Wrapping up and concluding, thank you for the attention. This is to me the thing. I think we're doing a great job science-wise, honestly. But I think that the thing that is missing right now is trust. Like the thing that we should work more towards building is trust in the research that we're doing. And that's going to be hard, but I think it's possible. But I see trust as coming across these three things that we should all have in mind at the same time. Making our science accessible, making it transparent, radically transparent, and having robust science be front and center. Thank you.
Thank you, Dan. That was great. Are there any questions either for Dan or Claudia? Alan, I noticed you had a question in the chat. But So I guess Alan asked, a lighthouse is placed in dangerous places to warn shipping to stay away. Are lighthouse activities a statement that science can be dangerous? So I guess referring to the WCRP lighthouse activity.
Yeah, a lighthouse is also meant as a way to conduct ships to a safe haven. So of course, the science itself, if weaponized from the wrong things, could be dangerous. I don't think there's any doubt of that. But it is also something to steer research positively towards positive outcomes.
I've got a question, if I may, for Dan.
Yeah, go for it.
Yeah, you're calling for transparency, and it seems to be at the heart of what you're doing, and that seems to be quite well established as a principle in terms of lab experiments. But we need to move outdoors, and there's a very long track record now, spanning, I think, more than a decade of, as far as I recall, complete success at making sure every single experiment is shut down if it's announced transparently, and every experiment that's been attempted that wasn't announced transparently has gone ahead. How do you reconcile the need to go ahead with important research with the desire for transparency?
Okay, you cut off, Andrew, but I'll answer anyway because I get your question. I think you're right. And there is this tension, and it's easy to take the lessons from this and say, well, at this point, might as well not be transparent, do the experiments we think are important, and then deal with the, ask forgiveness and not permission. I do think that that's how a lot of people think, but what I see is that would certainly help with the experiment you're exactly trying to do, but it's not going to help the whole field forever. Like, nobody cares then about the results of your experiment if the experiment is not being conducted transparently, and if people are not convinced. So
I'm more talking about the University of Washington.
No, I'm not talking. I'm not talking about anything in general. I'm talking about in general, right? I do think that the UNEA meeting, Mexico was one of the strongest proponents for a ban. I'm going to be there next week in Mexico, so I'll see better what they have to say. But I think that is a clear example of the fact that we could also be very close if people keep thinking. And again, I'm really not pointing the finger to anyone. This is a general reflection. If we're not more transparent, if we don't start being more transparent, somebody will do something stupid like a ban. I don't think bans are particularly smart. I'm on the record saying that. But also I feel like that's what's going to happen if people feel like we don't trust the public enough to be open. On the other hand, we should also be much more vocal in defending scientific integrity and scientific freedom, which means if somebody thinks that their experiment is scientifically important, they should say that. We say that a lot in the commentary. We should be more open to defending those experiments, and as a community say, this experiment is important for science. If it wasn't called an experiment about geoengineering, it would have gone on, because people do experiments that involve modifications of the outdoor environment all the time. There are tons of examples. We cite a lot in the commentary. Therefore, we should be way more open also, and be more forceful in defending the concept of scientific freedom when it comes to the experiment. But if we are not, we also don't try to be transparent, we're going to keep banging our head against the wall.
James, did you want to chime in?
Sorry, not beyond what I just said there. I just thought that, you could also just point to the reaction of Mexico or the reaction of the city of Alameda when you saw experiments or deployments go forth without advance notice. So I don't have an opinion on it one way or the other. I'm just not quite sure what the appropriate model is based on what we've seen.
I think we're all learning, and there's really no blueprint for this. But both Mexico and Alameda, their main beef, and we can keep arguing until we don't have a voice anymore, that those were completely harmless. in the case of Mexanta, they were just plainly stupid. But anyway, they were not going to do anything. They were not going to have any environmental impact. And what people were concerned with was the fact that they didn't feel included and involved right in the decision and in the process. So maybe that's the way forward. And if the experiment had been prohibited, even if there would be perfect transparency, it would have been so much easier in a way to argue more strongly in favor of scientific freedom of research compared to what happened, because then the discussion ended up being around transparency. So if we move first on that, I think it's better. But again, that's just my opinion, and I don't have perfect blueprint for this as well. And I'll respond to Greg later. Then I have to leave because I have another call that I was supposed to be in 4 minutes ago. Yes, absolutely. I think I made it clear. Climate modeling should be to the same demand of data transparency. I mean, we do make our modeling available. And as I said, I think we're trying to make an effort to also explain much better the choices behind the scenarios that we do. And I'm also trying to convince people to sort of start doing pre-registration of modeling experiments so that people cannot say, oh, Claudia made the experiments she did because she had a plan before and she threw away all the experiments that didn't work. As an example, Claudia, don't feel picked on. But it's the same for us, right? That's why for the new GeoMIP experiment, we put it out before we did any kind of experiment, actually. So yes, climate modeling should be subject to the same demands, and I think we're trying.
Okay, thanks.
Really need to go.
Yeah.
Thank you.
Yeah, cheers. Are there any questions for Claudia? I noticed there are a few in the chat. Were you able to answer them?
So far, yes, I think.
Okay.
If there's any more, then feel free.
Yeah, Greg, go for it.
Yeah, thank you. I'm afraid I came a little late to your talk, and you were concentrating entirely on the RCP, the RCP
8.5.
Yeah, which is the worst case scenario. And I understand, I think that was sort of the point, that you have to, if you're going to wait a long time, if you don't do good at, if you're very slow on mitigating, then and depending on SAI to save you, it's not maybe going to work. But that is such an extreme example of the behavior of civilization that, I mean, what about just a middling thing? One of the
idea that we had was not to say this is like a likely scenario. So we wanted to check whether in principle this irreversibility can play a role, and to check if something happens in principle, especially if you don't have right now the means to make a huge ensemble to check out noise or whatever, is to start with a big impact, like a lot of CO2 and a lot of SAI. Because if you don't even find this, let's call it irreversibility, even then you don't have to look for it under more modest scenarios. So this is not meant to be like, what people would maybe call a policy relevant scenario in a more narrow sense, but more a proof of concept.
Okay, thank you.